a cool start is all it takes. So in this song, the first step is so essential. Like it's so tricky and like interesting, and also like that simplifies the problem a lot. After that, it's pretty still and easy. So guess what the first step will be? Okay, okay. So let me show you. This sum from k equals to 1 to infinity minus 1 to the power k minus 1, and this is digamma function of 2k minus 1 by 2k minus 1 over here. Now the fact that there's this alternating term over here, that will, and also there are these just odd numbers, will basically help us to turn this into an easier thing. So, right? So, okay, let me show you. So this thing over here right now is like, first of all, positive 1 with digamma of 1 over 1, and then some with now negative 1 with digamma of 3 over 3, and then positive 1 with digamma of 5 over 5, something like that, right? Minus 1 digamma of 7 by 7, right? Okay, so this is the sum. But also, like just like this sum, like there can also be another sum, right? Like this one. Okay, this with like I, and then again like minus okay, then I square, which is minus 1, and then again multiply by I, which is like minus I with 4, and then again multiply by I, which is again 1 with 5, and so on, right? Okay, and now for this sum, if you just take a real part of this sum, you're gonna get the first thing over here, right? If you just take the real part. So basically what I'm trying to say is I can actually write this sum as just the real part of uh sum from n equals to 1 to infinity of I to the power n minus 1. So basically this I to the power 0, I to the power 1, I square, I cube, I to the power 4, right? So I to the power n minus 1, and then diagram of this is just n by n, right? So basically, like this thing over here is just the real part of this nicer sum. The nice thing is now there's just n, and that's much easier to deal with than when there was that 2k minus 1. So that's the interesting thing. Even with 2k minus 1, it's like the same, almost the same thing. Like all the details now that come later on can actually be done for like the way as it is, but it's easier to have it. And so okay, so I think that was a cool thing. Now we can just do it in a normal way. So now what we will do is I'll first write this diagram of function as minus of Wilmer-Masoni constant plus n minus 1th harmonic number, right? If I do that, we'll have Um, yeah, minus a whole imaginary constant plus n minus 1th harmonic number. And I will also change this 1 over n as integral from 0 to 1 of x to the power n minus 1 dx, okay? And yeah, there's a reason for that, you will say. And now I can write this as real part of integral from 0 to 1 and sum from n equals to 1 to infinity. This now becomes minus gamma times ix to the power n minus 1 dx plus integral from 0 to 1 sum from n equals to 1 to infinity. This is as n minus 1 ix to the power n minus 1 dx. Now this is basically a generating function, right? So this is basically a generating function like for the harmonic number, and we actually know that let me write in red. The sum from let's say k equals to 0 to infinity of as k, that's what over here, because there's n minus 1, x to the power k is actually minus ln of 1 minus x by 1 minus x, right? We're gonna use this standard generating function, and if we do that, what we will get is okay, real part of integral from 0 to 1 minus gamma. If I use geometric series, I will have 1 by 1 minus ix, right? A by 1 minus r dx plus integral from 0 to 1. This is minus ln of 1 minus x by 1 minus x dx, right? Sorry, ix, not just x. Mm, in this case, there's ix, so 1 minus ix by just 1 minus ix, right? Okay, now this will be okay. Now I'll just take the real part first. Okay, first of all, let me just rationalize this and take the real part. Okay, so that I just have to integrate the real part and not the whole thing. So this becomes 1 plus ix by 1 plus x squared dx, right? And now for this one, um for log, okay, let me write minus sign in front though. Okay, log of a complex number is basically the log of modulus plus I times log of the argument, right? So over here, so log of modulus is this is square root of 1 plus x square. The log of argument, and then it's like plus I times like tan inverse of the argument, which is basically minus x, which I can write as minus I times tan inverse x, right? It's like in the fourth quadrant, so I can do that. And do you see what I mean? Like basically the log of a plus ib will just be the log of the modulus, which is, let's say, if this can be written as uh r e to the power I theta, then we will have log of r e to the power I theta. So this is log of the modulus plus uh this I theta, right? Where this theta is like tan inverse of b over a, right? So that's what I'm talking about. This is log of modulus plus I times tan inverse of the angle. So yeah, using that thing, I can write it like that. And now this 1 minus ix, I will write it as 1 plus x square and then 1 plus ix dx. Okay. Now we'll just take real part, and this becomes an integral from 0 to 1 minus gamma by 1 plus x square dx. The next term is purely imaginary. And now again, there's this minus sign. And now, okay, so I can write this as minus half integral from 0 to 1 ln of 1 plus x square by 1 plus x square. Let me just confirm if there's any sign error, I guess no. Yeah, I think so. I think there isn't. Okay, and then after that, there's this uh plus I integral from 0 to 1. Oh, wait. I have to take all the real. I first have to take all the real things, right? Okay, so now in this product of this log of something minus I, and then this product, all the real terms that I get is basically the product of two real terms, right, with one, and the product of two imaginary terms, which is basically there will be a plus now because of I, and then x tan inverse x. Okay, so that's the thing. And yeah, 1 plus x squared dx. So this is the real part. Before I proceed ahead, let me just check signs I have right now are correct or not. Before I proceed, just a second. Mm, yeah, I think it's correct. Okay, that's good. So yeah, let's proceed ahead. So integral from 0 to 1 minus gamma by 1 plus x square or dx. Now this becomes minus half integral from 0 to 1 ln of 1 plus x square by 1 plus x square and minus integral from 0 to 1 x tan inverse x by 1 plus x square dx. Now I can actually get the second integral from the first integral while I use the integration by parts. So let me show you how. So 0 to 1 minus, now okay, this just becomes minus gamma times pi over 4, right? Yeah. And minus, this is half times, if I use integration by parts, this is ln of 1 plus x square and then tan inverse x, right, from 0 to 1, and then plus half. So then 1 by 1 plus x square times 2x, because that's derivative, and then tan inverse x, right, dx. Now the next thing, the last term is just uh, minus integral from 0 to 1 x tan inverse x by 1 plus x square dx. Now this just becomes minus gamma pi over 4, and this thing over here is minus half times uh, ln 2 with pi over 4, and at 0 it's just 0. Okay, and now this thing is just plus integral from 0 to 1 x tan inverse x by 1 plus x squared dx minus integral from 0 to 1 x tan inverse x by 1 plus x squared dx. And notice that these two are same and they cancel out. That's actually a pretty interesting and good thing. And after that, what I'm left with is minus gamma pi over 4, and this becomes minus pi over 4 ln 2 over 2. If I take minus pi over 4 common, I have gamma plus ln 2 by 2, which is, I think, is the answer. Minus pi over 4 gamma plus ln 2 by 2. So over here, the interesting thing was how we could actually change this sum at like odd indices to like sum with all the indices, right? And I think that was pretty interesting. And after that, we just used the definition of digamma function, the generating function for harmonic number, and then taking the real part and like integrating that using integration by parts and things like that. But yeah, I definitely hope you enjoyed this integral. This was a nice one. So thanks for watching, and I look forward to seeing you in the upcoming videos too.